The next important LAN networking protocol is the Spanning Tree Protocol, or STP. STP is a layer 2 protocol that runs on bridges and switches. While bridges are rarely in use anymore, switches are used extensively in local area networks, and most all layer 2 switches have spanning tree enabled by default. In this topic, we'll begin with a discussion of how switches that have redundant links update their MAC address table and resolve issues with the loop formation. We'll then look at the importance of STP in redundant networks. We'll also look at the enhancements of STP and various types of STP. And at the end, we'll look at a sample log entry that the security analyst can use to help identify or correlate attacks on the network that might affect spanning tree. Study the diagram shown here that shows a simple portion of a data network. The two hosts can communicate between each other by sending packets between the two switches. Let's say host B sends a ping to host A. Now assume that there are many more hosts connected to switch A and many more hosts connected to switch B, and that the network architect wants to increase the bandwidth and fault tolerance between the two switches. This could be achieved by adding one or more cables between the switches. In this example, a cable is added between the switches on ports Gigabit Ethernet 1/24. Notice how adding this cable created a single layer 2 loop comprised of 2 switches, 2 cables, and 4 ports total. Layer 2 loops can be larger or smaller and create the benefits of fault tolerance, failover, and additional bandwidth, but watch how they create a new problem. Initially in this example, let's assume that spanning tree is not present. So what happens if any computer like host B sends out even one frame that's a broadcast, directed broadcast, or multicast frame? Assuming all ports on both switches are in the same VLAN, switch B forwards the broadcast to all ports connected to the switch. The router will not forward the packet, as layer 3 routers don't forward broadcast frames by default. The outside network on a different router interface will not be affected at all. Switch A receives the packets and then forwards the packets to all ports with the active interfaces. Host A will receive the broadcast, which is initially not a problem. However, note that switch A is sending back the same packets to switch B. Switch B will then send the same packets back to switch A, and the process repeats itself over and over, on and on, very quickly. This creates a broadcast storm, which is a major problem for any layer 2 switch network. The entire LAN will become literally unusable, as the switches will waste all their time sending the packets around in a loop over and over without the capacity to forward any productive traffic. This problem was recognized decades ago when bridges were first created. The first solution created to solve this problem is the Spanning Tree Protocol, which locates the loops and stops the loops. Spanning Tree even has the capacity to find loops within loops if they exist in the LAN topology. The Spanning Tree Protocol was originally developed by Digital Equipment Corporation, a key Ethernet provider, to preserve the benefits of loops while eliminating their problems. Digital's algorithm later was revised by the IEEE 802 committee and was published in the IEEE 802.1d specification. The protocol that Spanning Tree uses is called a Bridge Protocol Data Unit, or BPDU. The word bridge in the name is still used even though BPDUs today run almost exclusively on switches. All switches send BPDUs every 2 seconds on all their ports, and all the switches work together to locate all loops and stop all the loops. To prevent loops in the network, first a reference point is needed, which is called a root bridge. A root bridge is the logical center of the spanning tree topology and is elected by STP. In this example, the elected root bridge is switch A. Therefore, all ports on switch A will be in the forwarding state. All paths that are not needed to reach the root bridge from anywhere in the network are placed in STP blocking mode. In this example, note that only one port is needed to stop the loop. The Spanning Tree Protocol calculation occurs when the bridge is powered up and whenever a topology change is detected. The calculation requires communication between the spanning tree bridges, which is accomplished by using the BPDUs. The Spanning Tree Protocol designates a loop-free subset of the network's topology by placing those bridge ports that, if active, would create loops in a standby blocking condition. Blocking bridge ports can be activated in the event of a primary link failure, providing a new path through the network. Note that if a cable is removed, there no longer is a loop, so Spanning Tree will not block any ports. Since the original 802.1d specification, many enhancements have been added. Some are implemented to speed up performance, such as uplink fast, backbone fast, and port fast, while others are configured to increase security, such as BPDU guard, BPDU filter, root guard, and loop guard. There are also other mechanisms that are not directly related to STP, but can be used to complement STP operations like UDLD. Today there are various flavors of STP, such as the IEEE specs of 802.1w Rapid STP, 802.1s for multiple STP, or the proprietary vendor extensions. As a security analyst, what suspicions can be determined by looking at this log information? This log entry shows a MAC flap notification message with the MAC addresses in VLAN 10 flapping between ports gigabit 1/1 and gigabit 1/2 on the switch. There could be various reasons for this event being triggered. For example, if there's an attacker on port gigabit 1/2 trying to spoof the MAC address on the host on gigabit 1/1, then there's a possibility that the switch generated the log message. It isn't always an attack which could trigger this kind of event though. Sometimes in networks with redundant links, due to misconfigurations or interface flaps, STP might toggle the redundant links, which could also have caused the MAC address flap. In this scenario, a security analyst can use their knowledge of STP to analyze the log information and identify whether it's a valid attack or some other type of network issue. Overall, a security analyst can narrow down the issues a lot faster with the proper understanding of the protocols and the network devices, which can save time while identifying or correlating attacks on the network infrastructure.